So in the last lecture, we talked about the quantum Hamiltonian. And although we talked about the part Hamiltonian, we haven't spoken about the states, the eigenstates of these Hamiltonians. It turns out that the eigenstates of the Hamiltonian that we talked about, um, they are they they have the interpretation of particles. So we are going to talk about the particle states. So in analogy with the simple harmonic oscillator, we are going to first define a ground state. In quantum field theory, the ground state is often referred to as the vacuum state. It is a state without any particles. And it's defined to be, it's written like in the Dirac bracket notation, has a zero in a ket. And it's defined to be that state which is annihilated all the annihilation operators. So this is zero for all values of the 3 momentum k. So once we have defined that to be the ground state, let's just ask the question, what is the state where one of the creation operator acts on the ground state? So the question that we want to ask is that, is this an eigenstate of the Hamiltonian? Well, let's find this out. Let's apply the Hamiltonian operator on this state. So H acting on K. Now we have an expression for H. The expression for H is d cubed of K by 2 pi cubed 2 of EK. So these should all be prime because these are the indices that we are integrating over. And then we have the number operator A dagger of K prime, A of K prime, acting on the state which we are writing as K. But this state is nothing but A dagger acting on the vacuum. So we can write this as, this whole thing acting on A dagger of K acting on the vacuum. And then what we did is that we just commute these two using the canonical commutation relationships. And if we do that, what happens? We get the usual dk prime, the measure, and then A dagger stays as it is. And then what here we get is the first term is A dagger of K, A of K prime acting on the vacuum, and then plus 2 pi cubed 2 of EK delta cubed of K minus K prime acting on 0, the vacuum. Now, this is an annihilation operator. This acting on the vacuum gives me 0. So the first term drops out. So as a result, what we have is, this thing multiplying this thing. But here we see we have a Dirac delta function. So we can do that to do this integral, and then everywhere we had a K prime becomes a K, and therefore we get, over here, we get 2 pi cubed 2 of EK, and then we have EK, and here we have then let's write all these constants. 2 pi cubed. There's another factor of 2 of ek. And then we have a dagger, which is this thing. Now the argument just becomes k acting on the vacuum. And now this, now this 2 pi cubed cancels with this 2 pi cubed. This 2 ek cancels with this 2 ek. And therefore what we have is E of k acting times the state k. So the left-hand side was H acting on k. So this is the right-hand side is Ek acting on k. So yes, the state that we created is an eigenstate of H with energy eigenvalue Ek. And let me remind you what Ek is. Ek is square root of 3k squared plus m squared. So we can now ask the follow-up question, is that if we have two creation operators, say one with momentum k1, another with momentum k2, acting on the vacuum, so we have a state that is labeled by momentum k1 and k2, then what would be the H eigenvalue of this state? Now, it is a very easy exercise to show that H acting on this state will give us an eigenvalue which is the sum of the two energies associated to K1 and K2. And it is this very important property which tells us that we can interpret this state as a state with two particles two relativistic particles, with energy with energies E of K1 and E of K2. And of course, it follows that this would be, it follows that this would be a state with one particle with energy E of K. Of course, we can have as many particles as we want. So for example, we can have a state with, say, n particles of arbitrary 3 momentum. And so this state could be created by applying n creation operator on the vacuum. And the energy of this state is simply given by the sum of the energies associated with each individual 3 momentum. And therefore, we can think of this state as having n particles. So, we had to impose the condition that if the commutator of a dagger of 2a daggers is 0. You might think that this is not a very important commutation relationship, but it is. And what it means is that suppose if I take a state which has two particles with momentum k1 and k2, of course this means that I have a dagger of k1 times a dagger of k2 acting on 0 on the vacuum state. But this is Since these guys commute, I can write this also as a dagger of K2 times a dagger of K1 acting on the vacuum state. And therefore, this is equal to K2, K1. So see that this state and this state are the same state, and they're symmetric under the exchange of the particle 1 and 2. So that means that these states are bosonic states. These states satisfy Bose-Einstein statistics.